core to this computer. Okay. Yeah. All right. So let's dive into the coding portion. So like I was saying, what I kind of want to go over is just two very simple kernels that are relevant to ML. So the first one I'm going to go over is vector addition, which is just you have two large buffers and you want to add the elements element-wise in both of them. And then after that, I'm going to go over matrix multiplication. And then so we're going to go over naive matrix multiplication kernel and then like one or two optimizations so you can kind of get a taste of the trade-offs and things that we want to think about while programming these kernels. Um, okay, so first of all, let me start with vector addition. Actually, let me start with have all of you guys seen C, C++ like syntax before? Okay, awesome. So hopefully this shouldn't be too unfamiliar. But we're just going to start off with a simple uh like how would we implement this vector addition on the CPU? That's just what I want to start off with here. So simply just we have our main function making two buffers of 1 billion elements, filling X with 1, Y with 2. And then I'm calling this add routine, which is just going to do exactly what you expect. It's just linear time addition between the two buffers. And then I'm also timing it here, so just we can see the time as we go, um, which should be going down. So let me just run this and then compile, and then let's run it. So it's not going to be that fast because obviously we're doing a linear operation over 1 billion elements, but there you can see it worked. So yeah, that's your CPU vector add. Now, if you notice, this is like a very parallelizable operation because none of these indexes I depend on any of the other ones because we're just adding them element wise. So we should just be able to do them all in parallel. Um, and that's exactly what we're going to do with the GPU version. Uh, so I'll try to sort of introduce this step by step. So the first thing we see here is our add function, except this time it has this global keyword. And essentially what that means in CUDA is that this is a function that's going to run on the device. And when I say device, I mean the GPU. So in CUDA, the terms are host and device for like the CPU and the GPU. So whenever you mark a function with global, that means it's a device function. So it's a kernel. Um, and it's going to take the same thing, the size, and then the two buffers. And now instead of I coming from this for loop, it's actually going to come from like these special variables here. And this is kind of where the block thread hierarchy comes in. So that kind of allows us to like build these indices that we can use to know what thread we're currently in. Um, so in this example, like we're going to be launching a bunch of blocks of like let's say like 256 threads. So if you imagine like a sequence of these blocks of 256 threads, how do we find out like what thread we're in if you consider like the global index? Well, it's just going to be the index of the block that this thread is in times the block dimension. So that gets us all the way up to the current block. And then the thread index is the index of the thread within that block. And these are special variables which you can just use, and they will like these variables will have the values of like whatever block or thread that code is being executed in. And then we just have this guard. So like let's say we launch more threads, like if we launch more blocks or threads than is actually needed for the computation, we might have some extra threads being executed. So if this I is greater than or equal to n, we just return out of the function. Otherwise, we just do y equals x plus y. So we just do the add. Um, and then there's also some stuff changed in main. So we're still doing the same thing here where we're initializing the two arrays. But then we also have to allocate memory on the device. So that's what is going on here. So I'm creating these two pointers for the device X and the device Y, and then calling CUDA malloc, which is going to populate this with a device pointer, so a pointer to memory on the device or the GPU. And it's basically just like malloc. You all know malloc. And yeah, so we're gonna allocate X and Y, and then we're gonna do a mem copy. So you can kind of see it's like CUDA has its own version of all of these functions. So we have CUDA mem copy, and that's going to copy the data from X, which is on the host, to DX, which is the device pointer. So we're basically just copying these two buffers to the device. Uh, that way we can, actually add them. And then here is where we see what's called the launch configuration. So when we actually run a kernel, we have to specify how many threads are going to be in each block and how many blocks we want. So that's what's going on here. So I just arbitrarily said, okay, we're going to have 256. Uh, we're going to have 256 threads per block. And then the number of blocks is just going to be n, which is, a billion, and we're going to ceiling divide it by block size. That's what this is doing. That way we make sure we have enough threads to cover n. And then yeah, then we call the add function. This is the syntax for calling a kernel. So it's these like triple greater than less than, and then we specify the number of blocks and the number of threads per block. And then as you can see here, I'm passing in the device pointers because this has to operate in the device memory. Then after we call this CUDA device synchronize, which is going to like basically block until this add like kernel is done. Because if we didn't have that, it's non-blocking, so it'll just continue. So we actually like want to fully wait for that to finish, and then we want to do another CUDA mem copy to copy the results back to the host. That way we can actually like read it and do whatever we want. And yeah, so that's basically what the add kernel looks like. Um, this is kind of like if you understand this, the rest of it is pretty much like follows. So I just want to make sure like does anyone have questions about this or like any confusions at all? Um, Pretty much got it. Okay, cool. And yeah, this is like one of the most important things to understand, kind of the way you use these variables to specify what like, index in the computation you're trying to do. Um, but yeah, so let me run this. And then here, instead of G++, the compiler is NVCC for compiling this CUDA code. So, and then we've specified this, which is the architecture. So Colab is using these T4 GPUs, so I had to specify this, otherwise it was throwing some errors. But yeah, it's just compiled like any other code. And then gonna run the add kernel. So in this case, it's not going to be much faster than the CPU. And the reason for that is because even though this is a very parallelizable task, we haven't increased the elements enough to see like the speed difference. And also, this is like a task that has very low arithmetic intensity, which is another term in GPU programming, which basically means for every memory load that we're doing, we're just doing one add, which is very little work per memory load. So this is like a very memory bound kernel. So like most of the time is just spent like transferring these buffers to the device and then like loading them here because these are being loaded from global memory when we're adding them, right? Um, but yeah, that is the most basic kernel, the vector add kernel. Um, So next I'll go over matrix multiplication. And this is kind of like the meat and potatoes, I guess, of GPU programming. So this is the CPU implementation. So basically what's going on here is that so I'm initializing this random number generator in C++, and then M, N, and K is going to specify the shape of the matrix multiplication. So the matmul we're going to be doing is like A times B equals C. C is the output. So A is going to be M by K, B is K by N, and then the output is going to be M by N. So basically M is the outer, M and N are the like outer dimensions, and then K is the inner dimension. Um, and so yeah, we're gonna initialize three buffers for A, B, and C. So A is obviously going to have m times k elements, B k times n, so on. And then we're going to fill them with random numbers. And then C, we're just going to zero initialize it. And then we're going to call this matmul routine on the CPU, which is just going to do your basic like just implement the definition of a matrix multiplication. So this I and J, you can think about that as like, okay, what element in the output am I currently computing? And then for each element in the output, it's going to be a dot product of the corresponding row in A and the column in B, right? So that's what this is going to do. So this is looping over K, the inner dimension. It's computing that dot product. So initialize it to 0, and then this is one thing that you kind of might want to get used to, is the way that like we're indexing into these buffers is like I haven't defined it as like a 2D array. So we're indexing it like this, where this is the row we want, times the number of columns plus like the column we want. So this is equivalent, like, so that's the same thing as like doing A, I, K, right? Except we have to manually, multiply the row by the width, um, so that we get to the row that we want, and then the offset within that is the column. Um, so yeah, does everyone understand what's going on here? Okay, cool. Yeah. And so then we write it back to C as the output. So that's your CPU matrix multiplication. And this should be pretty slow. Um, so hopefully this will be a good motivating example. Um, yeah, so it's not that fast. Um, so now let's parallelize this, right? So obviously every position in C that we're writing here. So this outer for loop is looping over every position in C. None of those depend on each other, right? So we should be able to compute every element in the output in parallel. And that's exactly what we're going to do. So here's our naive matrix multiplication kernel. So again, I've just written the shapes up here. So the inputs are the shapes, the two and the three buffers, right? And so again, we're gonna get our thread ID. So we've launched many blocks. Each of those blocks has some number of threads. And I basically just want a variable that's going to give me what is like the global number of that thread in all the threads that we've launched, right? So again, that's this. And also, if you don't understand anything, feel free to interrupt. Um, and so then we need to specify, okay, we're in this thread right now. Which element in C is this thread going to be computing? So that's what this row and call variable is. So uh, the width of C is n, right? Um, so basically, the way I've defined it here is the row in C that we're going to be computing is like the current thread index mod n, and the column is divided by n. So if you think about like, for example, TID is 0. So like that's the first thread. It's gonna be the row and call is gonna end up being 0, 0. So thread 0 is gonna be computing the 0, 0 element in C. Now if for thread 1, it's gonna be 1, 0, right? So the row is gonna be 1, the column is gonna be 0. So it's gonna be computing the value right under that, right? So and then you can kind of see it, it'll go column by column as the thread index increases. So it's basically just a logical mapping from, we're just taking our 1D thread index and mapping it to one of these 2D points on C, right? Does that make sense to everyone? Okay. And then here we have another guard just to make sure we're not doing anything outside of the size of C, right? So if the row or call we computed is greater than or equal to, M or N, we just return out. And then what we've basically done is these two outer loops, these have now been parallelized over all the threads, right? Because we're computing the row and call, which in this case it was I and J from the thread index, right? So the only work to do is the inner loop. Each thread has to do the dot product of its row in A and its column in B, right? So that's exactly what this is. So uh, loop over the inner dimension, and this is the computation we're doing, right? So we're going to do the row from A and the column from B and dot them together. So that's exactly what this does. And then we write it back to C. And so this has basically, removed those outer two loops, right? Because now those are being done by the threads in parallel. So this is that. And then I just wrote, so the launch code, let me go over the launch code quickly. So again, randomly initialize all of this, fill A and B with random numbers. In this case, I'm going to do also the CPU map mul so we can check. And then here again, we're seeing CUDA malloc. So we're mallocing for each of these buffers on the GPU. Uh, and then we're doing a mem copy of A and B so we can actually get that data on the GPU to work with it. And then when we launch the kernel, we're launching it with 256 threads per block, and then we calculate the number of blocks we need with this time m times n, because that's the number of, individual elements that we need to compute in C, and each thread is going to be doing one of those. So then we divide that by the number of threads per block, and that gives us our number of blocks. And then we launch the kernel. And then also, I think I may have forgotten to include this in the vector add, but we also free these buffers at the end, which is the correct practice. And then yeah, after the computation, again, we do this. We copy C back to the host. So C GPU is just I've made two buffers for the result from the CPU and the result from the GPU. Yeah, and then compile this and look. So we should see that, the GPU is significantly faster. Like you can see that's a massive improvement, and it's done the computation correctly, which is good. Um, okay, so that was a 1024 by 1024. So what if we make them even bigger? Um, so here we're gonna do 4096. So nothing has changed. We're still going to use the naive map mul. I just want to show you kind of how, you know, even the GPU can get slower as we go to these larger sizes. So yeah, like now we have, around 3 seconds on the GPU. Um, and on the CPU, this actually takes minutes. So I actually had it before, but I just removed it because it just took too long. And so this is good because it kind of gives us some room to do some optimizations that I want to show you guys. So the first optimization we're going to talk about is global memory coalescing. So before I dive into this, just want to make sure, like, are we all on the same page right now? Like, does everyone understand the naive matrix multiplication up to this point? Okay, awesome. Um, so the first optimization we're going to do is global memory coalescing. And the idea here is that essentially, due to the way the hardware is implemented, whenever these threads access consecutive locations in global memory, uh, the hardware can actually do something called coalescing. So, like, if 32 threads are accessing 32 consecutive locations, and then you have like that's 128 bytes, um, the hardware can like turn that into one memory transaction where it just loads that chunk at once. So basically the takeaway is that whenever possible, we want the threads to be accessing consecutive locations in memory. We don't want to like be accessing them with a stride. So like thread zero accesses like address zero, thread one, address 64, thread two, 128. We don't want something like that. We want them to be accessing consecutive locations for, optimality. Uh, so right now, with the way that we have it set up, um, consecutive threads are accessing different rows of A and the same column of B. Um, so what I mean by that is kind of what I was talking about when I was explaining the first naive kernel that we did. So right now, uh, this is kind of the picture I want you to have in your mind. So thread ID 0. So this first thread that's computing this 0, 0 element in C, it's accessing this row of A and the 0 column of B, right? And then thread ID 1, uh, as we saw from the way we implemented the naive kernel. So thread ID 0 got 0, 0 in row call, right? So thread ID 1 gets 1, 0. So thread ID 1 is computing this element right here. So it's accessing, row 1 of A and column 0 B. And when we think about what A looks like in global memory, so it's just a flat buffer of floats, right? So thread 0 is going to be accessing right here, right? And then go over K floats, and then thread 1 is accessing K floats later, right? Because it's going to access this float, right? Um, so do you all understand why that's an issue? Uh, because the threads are not accessing consecutive locations memory. They're going to be accessing locations that are offset by the size of this entire row, right? Uh, so what we would actually like is something more like this, right? Where thread 0 and 1, which are consecutive threads, right? We want them to access consecutive memory. So we'd actually like them to load the same row in A, right? Because they're going to be loading this. All of these floats are consecutive, right? In memory. And then load different columns because these two, it's going to be loading these two, right? And these two are consecutive. Um, because it's a row major in memory, right? So each row is laid out horizontally. Um, that it's a little confusing, but did everyone kind of get what I'm trying to say with that? Okay, awesome. So that's just like a very like simple optimization we can do to enable coalescing. So all we're gonna do is where before I had row was the thread ID mod n, I'm going to change that to divide, right? So now 0, 1, 2, 3, all the way up to n, that's all going to map to the same row, right? So if we think about thread 0, now thread 0, if we like TID 0 is going to get 0 in row and it's going to get 0 in the column, right? And the TID 1 is going to get 1 or it's going to get 0 in the row, right? 1 divided by n, and it's going to get 1 in the column. So that's basically achieved this, where our consecutive threads are now going to be computing along one row of C. So we're going to get this nice memory access pattern where we're accessing consecutive locations in global memory, right? Uh, so just with like, changing those two lines, can see that that already gives us pretty decent improvement just by thinking about how can we, optimize the memory access pattern. And that's like something you'll see a lot if you continue doing GPU programming. A lot of it's all about like compute and memory. So how do you optimize your memory access pattern, and then how do you do as much computation per memory access as possible? Because memory access is slow. So yeah, like you can see we got, around a 3x improvement, which is quite good. Um, okay, did everyone get that part? I'm happy to explain anything more. Um, okay, awesome. Uh, so for the last optimization that I want to go over, so this one's going to be a little more in depth. So feel free to stop me at any time during this. But now we're gonna make use of shared memory. So up till now, we've only been using global memory. So all of these buffers were allocated using CUDA malloc, right? That's allocating in global memory. And then we're just operating directly on them. So anytime we index into A or B like this, we're loading from global memory. And then this is a global memory store because we're storing to C, which is in global memory. Um, so the idea we're going to try and implement with optimization number 2 is that, okay, let's have a group of threads load some chunk of A and B into shared memory. So we're basically going to take a chunk of A and B, cache them in shared memory, do as much work as we can in shared memory, uh, then write the result, and then go to the next chunk, right? So basically the idea is we're kind of using the shared memory to like uh, we're going to cooperatively load, chunks of A and B into shared memory. And then basically we're operating as much as we can on this data in shared memory so that we touch global memory less. Um, so that's going to be kind of the idea of this. And this is a great picture from a blog post, which I'll show you guys at the end. But this is kind of like the picture to have in your mind. So this is C, right? A and B. And so we're going to be like, we're gonna introduce this new variable of like the row. So we're splitting C up into these kind of these block rows and columns. So like these are the block rows, these are the block columns. And then we're gonna have this block in A and B, and we're gonna load basically those like this chunk in A and this chunk in B into cache. Do whatever part of the matmul we can from the data in cache, and we're going to slide the block down the row of A and the column of B, and then continue. So once we fully slit it, then this group of threads will have calculated all their values in C. And that what that basically does is reduces the amount of times we have to touch global memory, right? Which is what we want. So I'll try to go over this slowly. So just defining a couple of things. So the size is 1024, the size of the matrices. Block size is going to be 16. And when I say block size, I mean like, so in this one he has 32 written, but our blocks are going to be like 16 by 16. So we're going to be caching like 256 floats at once. Um, yeah. And so again, here is our matmul kernel. Uh, so C row and C column. So kind of the thing to think about here is before we're having each thread is calculating one position the output, right? Now we're having each thread block so each thread block is responsible for a block in the output, right? So what row, like this is the C row and the C call is like these larger rows and columns in C, right? Of the block size, right? Uh so what which one is this thread responsible for? Well, it's the block index of the thread, right? Because each thread block is going to handle one of those chunks in C, uh, divided by the number of blocks per row. Uh, and when I say blocks per row, in this picture, it's like four, right? Because we can fit four of these blocks in one of the rows. Um, so that's just calculated by the size dimension divided by the block size, right? So yeah, this is going to give us our C row, C call. So now we've kind of identified, okay, what chunk are we in C for this thread, right? Um, and now we want to, and S row, S call is stands for shared, kind of is what I try to do here. But this is what index in A and B this thread is going to load. Um, and this will make more sense later. So now we're going to declare these shared memory buffers. So you can see this shared keyword. Basically, what that means is, okay, I want to declare this buffer in shared memory. So um, basically every thread in the block, like I said, will have access to this shared memory. Uh, so it's going to be block size times block size. So in his case, it was 32 times 32. In our case, it's going to be 16 by 16. Um, And then we also declare one for B shared. So we have A shared and B shared. So we're taking our chunk from A, putting in shared memory, chunk from B, putting in shared memory, right? Uh, and then what this is going to do is this is going to get us, so we're about to load these chunks from A and B. This is going to get us to the correct position in A and B, right? Um, so basically the position that we want to be in A, right? So like the pointer to A is here, right? So first we want to get to the correct block row, right? Um, so that's what this does. C row times block size. So block size, so uh, yeah. So like that'll basically bring us down to like the start of the right row that we want to be in. Uh, and then, okay, hold on. Let me try and explain that better. I don't think that made much sense. So C row is like what row we want to be in, right? For the computation of the current block. And then we want to multiply by block size times K because the width of each of these is block size, right? Or sorry, the height of each of these rows is block size. Uh, and then K is going to move us down, like times K is going to move us down all the way to the end. So C row times block size times K will move us all the way to the start of current block row, right? Um, and then in B, we're going to do a similar thing where we just need to get to the start of the current column. So the pointer to B is in the top right corner, in the top left corner, right? So then we add the offset, which is the column that we want to be in times block size, right? Going to move us over to the start of that column. And then for C, we want to be not just at the start of the correct row or the correct column, we want to be both, right? So for that one, we're going to add both. And you can see whenever we like want to traverse to a certain row, we always have to use the column dimension of that matrix, right? So for A, we're using K, right? Because A has K columns. For C, we're using N. So that'll get us to that'll basically get all our pointers to the position we want, right? So now our pointer to A is here. Our pointer to B is right there at the top of the blue row, and then the pointer to C is here because that's where we're going to be writing, right? So does that make sense, basically? Okay, cool. Um, Now we do the actual matrix multiplication. So we're gonna again loop over this inner dimension, but this time we're gonna loop over the block size. So this loop is actually what's moving our block. Um, so the number of times we need to move the block, so we just have, I less than k, I plus equals block size. So it's just moving the block, right? And then here we're loading from global memory, which is A, which is global memory, right? Into A shared. So this thread is responsible for loading S row and S call index uh, of A shared from the corresponding position in A. So that's basically all this is doing, right? Uh, so when each of the threads executes this, when each of the threads in the block executes this, we'll have loaded this entire chunk of A, right? Cooperatively. Each thread is only doing two loads, but when we're done, when all the threads are done, this entire block of A and B will be in shared memory, will be in these buffers. Because all the threads in the thread block share these buffers. Does that make sense? Like, can we kind of see what's going on here? And so then we call sync threads because we don't want, for example, thread 0 to do its two loads and then move on. We want it to do its two loads, and then we want to wait for thread 1 all the way to 255, all the threads in that block, in the thread block, to finish their loads so that everyone can see the same thing in shared memory, right? Because like I said, shared memory is shared between the threads, so we have to synchronize when we want them to all read the same thing. Um, so now we've loaded our chunks from global memory from A and B into shared memory A and B. Um, and then we advance the blocks. So for A, we advance it by block size. So A just moves from here to here. And then for B, it needs to be advanced by block size vertically, right? So for that we do block size times n, because n is the width, right? So it's gonna, go that many columns down um, until the block has been moved down. Uh, that's what this is doing. And then we do all the work we can with the data we loaded into shared memory, right? Uh, so here's the inner loop for the matrix multiplication. So for k equals 0 to block size, you can imagine it's almost like we're multiplying these two mini matrices, right? Um, So we're looping over the value of A times the value of B, adding that to temp, right? And then and notice how temp uh, is we're not accumulating the dot product right here, right? Right before this for loop, like we were doing before. We have it outside of here. So once the block once they've both slid across the entire like block row and block column, then this entire chunk in C will be done, right? Uh, so we write it. Um, and yeah, that is shared memory caching optimization. So a little more involved, but I think this really gives you a good idea of how you can use like shared memory in a smart way. And also, one thing to note is we also need the sync threads at the end so that we don't have some stray threads that start loading the next block while the other threads are still reading from that shared memory, right? So yeah, we have another sync threads here. Uh, so compile it. And yeah, you can see it's quite a bit faster. Uh, so which is nice. And here we're trying it with the larger dimension. So yeah, so you can see we're getting 310 milliseconds on this larger dimension. I believe we were getting like, yeah, 1247 here. So again, another pretty nice improvement. Um, but yeah, okay, so that's basically all the code that I wanted to go over. Uh, I have some references at the end here if you're interested. Highly recommend these two resources. So this is just the NVIDIA docs, the CUDA docs. They're pretty good. If you just want to read more in depth, I'd probably recommend starting there. And then if you want to learn more about optimizing the matrix multiplication or you're interested in that, this blog post basically goes more in depth. So the level that I introduced here with the shared memory caching, that's like the second level on his. And he goes much further. Like he does, there's many more things you can do to reach the level of, the actual routines that are actual kernels that are used in things like, PyTorch and stuff like that. Um, yeah, that's pretty much all I had. Did I want to ask again if anyone had any questions, I'm happy to answer them. Wrong.
So like on top of like scroll a little above.
Yeah.
Yeah, so the blue
Mhm.
comment, does that just declare a file name?
Oh yeah, yeah. This is just like some syntax in Colab. I actually didn't know you can do this, but it just like it's saying like write whatever is in this cell to this file. And then just compiling it here. So yeah. Yeah, any other questions? All right, that's all I had. Thank you guys.